Probably, it's pretty fast.
Yeah.
Oh,
Just period.
wait. Yeah, she did this, but, I'll send it to you.
I'll check on it.
I don't actually see where the links show up. I never see the links. So
Yeah,
you send it to me.
sure,
If you can send it to me, yeah.
Yeah, no doubt.
I'll make sure that, they'll post it, right at the,
I think it's supposed to be linked from the seminar website.
Yeah.
So when you go to the,
it's on Filson.
yes, but I think Shane links it from, if you go to the CMM website, it lists all the talks. And I think if you go to that, there should be a link to watch it. Yeah.
So you can also get direct link on which.
Yes, yeah, okay, yeah, but hopefully he also links it back to the website. Anyways, it is my deep pleasure to announce Dr. Jana Gevertz and welcome her here to Toronto to give a lovely talk in our Center for Mathematical Medicine seminar series. Thank you for adjusting to the earlier time. And we will have to end right at 1 o'clock today. So if we can, I'll have to cut the questions off. I'm sorry, because I have to go. But anyways, Jana will be talking today about smart data, smarter models, enhancing the predictive power of mathematical models of cancer. Thank you, Jana, for coming.
Thank you, Kathleen, for having me. Zoom world, do you hear me okay? Do I have a way to know you hear me okay? Like watching? Yes. Okay, no, we're good. We're good. What? No. Oh, that okay button. It's mine. Well, I hit okay on mine, so it's not mine. Okay. Thank you. We're good. Okay. Hi. So really what motivates all my research is this idea that we know cancer dynamics and treatment response is incredibly heterogeneous across patient populations. So my sort of interest in this heterogeneity goes back to when I was an undergrad, and my dad was diagnosed with stage 3 cancer. And he had a colleague 15 years younger than him that got the same diagnosis. They went through the same treatment protocol, the standard CHOP protocol. And my dad ended up being what you call a super responder to the therapy. So after 1 round of CHOP, there was no evidence of disease left in any of his blood markers. His doctor didn't know what to do, so made him go through the minimal 4 rounds, and he's been in remission ever since. His colleague went through 8 rounds, never responded, and died a year later. And ever since then, I've wanted to understand why you could take 2 people with the same response and get, same diagnosis and get such different response from them. But I also knew that for me, I wasn't going to go to medical school. I wasn't going to study cancer from that perspective. It ends up the same semester that this happened with my dad, I was taking mathematical biology. So with Eduardo Sontag back at Rutgers. And it became clear to me that mathematics is a very powerful tool for trying to understand complex biological and clinical phenomenon. But what's become more increasingly clear is that for these models to be of any use at all, right, they need to be driven by data, but not all data is created equal. So my research really has 2 main threads. So one is, if we do have a model, how do we make robust predictions out of that model that are not highly sensitive to functional forms, parameters, underlying model assumptions, but also how do we get the right data to inform our models? So I'm going to tell you about 2 different projects today, sort of one in each direction. And the first one is about the design of combination therapies. So when you're thinking about designing combination therapies, there's really 2 different questions you could be asking yourself. The first is, what drugs make the best combination partners? So this would be the idea of having like a big drug screen, and you're trying to select the best drugs to combine. But a second question is, you've already identified your drugs and you want to know the best way to combine them. So a dosing and scheduling question. And if you think from the perspective of pharma, right, this is going to be the question you're asking once you already identified your compound, right? So you already have a standard of care. You now have your new compound. You want to know how to best combine them. So this is the question that we were going to focus on, but I'm being very vague here when I use the word best. What does it mean to identify the best combination? So if you look in the literature, you'll often see the notion of synergy used as a way to search for combination drug partners. And in a way, it makes a lot of sense, because what synergy is supposed to do is measure what happens, measure what one drug brings out in the other drug. So effectively, it quantifies either the gain in efficacy or the reduction in toxicity realized only when the 2 drugs are given together. And the idea looks very simple. You have this notion of additivity, which is sort of characterized as being 1 + 1 = 2. If 1 + 1 gives you more than 2, you call it synergy. If it gives you less than 2, you call it antagonism. Sounds really basic until you realize that the definition of additivity has been, and I quote, at the center of controversy among leading researchers of the topic for the last century. And the reason is because despite the language, which sounds like, oh, I'm just adding stuff, additivity does not just mean adding the effects. And if you actually look in the literature, you will find an overwhelming number of divergent definitions of additivity. And to understand why this is so complicated, I'm going to paint an analogy for you, and it will literally be an analogy about painting. So here's the scenario that I'd like you to consider. I'd like you to consider two people. Person one can paint 40% of a room in 3 hours, and person two can do the same thing, but it would take them 4 hours. So now I want you to imagine you're thinking about how much of the room gets painted. So person one will put in their 3 hours of work. Person two will put in their 4 hours, and somehow they only paint 25% of the room. Well, they could have done 40% on their own. No one would argue this is an antagonistic relationship. And if magically 100% of the room got painted, they must have worked really well together. We'd agree it's synergy. What if I told you 60% of the room got painted? I would bet if I take a survey, if I had more people in the room to ask, right? Like, not everyone would agree. Would you call this synergy, antagonism, or even additivity? Is unclear. So I'd argue that's uncertain. And then there's a totally different way to think about the problem. You could also think of how much effort went into painting a certain amount of the room. So I want you to imagine 40% of the room got painted, and it took a combined 10 hours to do that. Well, they could have done that individually on their own in less time antagonism. If they do it in an hour, we'd all agree that's synergy. But what if it took 3.5 hours? Again, I want to argue that is fairly unclear how we'd classify that. And the real reason this becomes complicated is that at the extremes, synergy and antagonism are incredibly clear. But what you really have is an infinite line, and additivity is a single point on that line. Everything on one side is synergy, everything on the other side is antagonism. So because of that, where does that line get placed, or that point get placed on that line makes this a hard question. So now let's bring this back to combination therapies in cancer. So if you're going to look at the effects of combining two drugs, you might be interested in the output. So in the painting example, how much of the room got painted. Here, that's going to be tumor growth inhibition, right? The efficacy of the combination. So the oldest known concept for how to define additivity, if this is the way you're thinking about it, is Bliss additivity. And Bliss additivity just essentially treats the output as a probability and assumes the probability of the unions could be calculated under the assumption of independence of the events. So if you sort of achieve that threshold, then you're going to be additive. Any more effective is called synergy. Bliss is known to propose a very high bar on what gets classified as synergy. Within the same category, there's also this notion of highest single agent additivity. So in this one, you take the more effective monotherapy. That's your line of additivity. Anything more effective than the more effective monotherapy is called synergy. This is a very low bar for being called synergy. And this is just one way of thinking about the problem. If you think back to the painting example, you could also ask about the input, how much time you spent on it. So in the context of drug combinations, that's going to mean how much drug were you given related to the potency of the therapy. The oldest idea here is the notion of low additivity. This basically assumes there's a scalar that you could take the dose of one drug and get the effect of another drug, and it applies across the entirety of dosing space. So it could just like a constant multiple gets you from the effect of one drug to the other. What this looks like is parallel dose response curves. Low and Bliss people have been fighting since the 1930s about the right way to define additivity. They convened a meeting in the 80s or 90s to try to agree on a definition of additivity, and they left more sort of contentious than when they had started the meeting. So these people don't agree. And then to make things more complicated, we decided to wade in and introduce another way to think about additivity via potency, and we call this the lowest single dose metric, and it was meant to be really like a potency-based analog of highest single agent. So you find the more potent monotherapy, so the one that you give less drug to get the same effect. That's your additivity line. If the combination somehow is more potent than that, you'd be synergistic. Less potent would be antagonistic. So now you have these like very divergent ways to identify what additivity is. Each of these get assigned a numerical value. You need a way to compare across them. So the combination index is used for that purpose, and it's defined differently depending on your additivity metric. But the important thing is they're all defined so that a value of 1 is going to mean an additive combination. Less than 1 means synergy. The smaller, the more synergistic. Greater than 1 means antagonistic. So now we have a way to compare across these. That being said, there are other definitions of additivity if you go through the literature. So I don't want to claim I'm showing you every definition out there. And if you look at the years on these papers, you could see like these are not from the 1930s when Bliss and Lowe started. People are still really actively talking about this. And we're not going to go through any of these. But I want to say beyond having so many definitions, the definitions are used wildly inconsistently in the literature. So there's this meta-analysis from 2019 that basically said people arbitrarily pick a metric, even though each one has underlying assumptions that you can't really test about your data. Even worse is the predictions you make sensitively depend on the metric you used. So in this meta-analysis, they looked at if you took the same data but used a different additivity metric, and most of the labels would change. So you imagine that this really confounds the search for synergistic drug partners and synergistic dosing and scheduling. So this is the question that we were sort of wading into. And the first thing we thought when we did this is, well, there's no reason the Lowe and the Bliss people should be fighting. Efficacy and potency both matter. Yeah. That's definitely part of the dose, right? That's definitely part of the question of designing the optimal way to combine them, which is something we've looked at as well. But it does make the problem more complex because it's dose and it's scheduling. Yeah, correct. Go back. Go. No, it's not actually. So it's really just assuming that, so in Bliss, they effectively assume the probability of giving A or B is probability of A plus probability of B minus the product of the probabilities. So no conditioning. Yeah. Sorry about that. Thanks for telling us. Yeah, next time. So given that we didn't think there was one reason you should prefer efficacy over potency, they're both very important, right? The effect of the drug, the toxicity of the drug. Our first thought was, all right, well, let's bring multi-objective optimization into this. Oops, wrong one. So if you're not familiar with this, right, multi-objective optimization is just a way to optimize multiple objective functions simultaneously over your set of feasible decision vectors. So to make this concrete, let's forget synergy for a moment. Let's imagine you want to minimize tumor size and toxicity. On the horizontal axis, you have your allowable dose of drug 1. Vertical is the dose of drug 2 that you're allowed, right? It's very clear that you're not going to minimize tumor size and drug-induced toxicity at the same dose, right? So at least let's think preclinical over short time scales. The most drug will make your tumor smallest. But of course, if you're trying to minimize drug-induced toxicity, you shouldn't give the drug at all. So the question becomes, what does it mean to be a solution to a multi-objective optimization problem given this? So to answer that question, what we're going to do is take our points, which are in what we call design space, the set of possible doses, and map them into criterion space, which is a set of possible outcomes. So just to illustrate, if you give no drug at all, well, you have no toxicity, the tumor will be as large as possible. You give a lot of drug, you're going to have a lot of toxicity, tumor will be as small as possible. Every point in design space maps onto a point in criterion space. Criterion space is where we perform the multi-objective optimization. So what we're going to look for is what we call Pareto optimal points. And to understand these, we first need to understand what a non-inferior point is, and then we'll do inferior points and then non-inferior points. So this guy right here is considered an inferior solution for a minimization problem. Why? Because there's definitely other points in the space that make both your objectives smaller. You would never want this in your solution set. On the other hand, this guy right here is a non-inferior solution. Why? There's no point in the space that can make both objectives smaller simultaneously. So yes, we can make objective 1 smaller, but it happens at the expense of objective 2 and vice versa. So we call this a non-inferior solution. And the set of non-inferior solutions is what we call the Pareto front. And this is a solution, the set of solutions to your multi-objective optimization problem. Each point on the Pareto front then corresponds back to a point in the design space, which is a dose of each drug. And then you have a decision in front of you. You have to decide how you want to balance your competing objectives to pick a solution for further study. So if we go back to the notion of synergy, now we have to ask the question, well, if we're trying to optimize synergy, what are our actual objective functions going to be? So keeping in mind that we want one measure to be potency, one to be efficacy, but we're unclear about the definition of additivity, we're going to consider multiple definitions simultaneously. So for potency, we will allow ourselves to consider potency defined via low additivity or lowest single dose. And synergy of efficacy could be defined through one of the two metrics as well. So what that does is create 4 potential spaces in which to perform our optimization. We will do the optimization in each of the 4 criterion spaces. And then what we will do is compare outputs across these and try to look for consistency across those spaces. So if we can find solutions that are predicted to be Pareto optimal, independent of how you define additivity for efficacy and potency, we would like to think of that as a more robust prediction about optimally synergistic combinations. So we call this algorithm MOOCs-DS for multi-objective optimization combination.
Well, thank you. I was just wondering about your terminology, like when you say Pareto front, like when we hear Pareto in probability, of course, and actuarial science,
Yeah,
it's
notion.
same notion, like it's negative power decay.
Okay, yeah.
So is it right, like this curve which you showed Pareto front in the previous slide?
Yeah.
So it's a kind of negative power at
Yeah,
infinity. So this is the reason. Yeah?
Yeah,
Okay.
I like
So I go to try it.
Yes.
Thank you.
So what I want to do is show you what happens when we apply this algorithm to a real data set. So the combination we're going to look at is an immune checkpoint inhibitor, pembrolizumab, and an anti-angiogenic agent, bevacizumab. The truth of the matter is the details of what these drugs do don't matter for this part of the talk. All that matters is, right, the drug is given and it can pull down the size of the tumor. That's all that matters for this particular part of the talk. So let me show you the data that we had. It was 2 non-small cell lung cancer cell lines, one p53 wild type, one p53 deficient. So for both of these, we're going to have a control data set, the pembro given as a monotherapy, the bevacizumab given as a monotherapy, and the combination therapy. And you can just take a quick look at the data and see it's quite clear that the p53 deficient cell line responds much more strongly to this drug combination than the wild type. So we'll look at this one for the sake of the talk. We've looked at both in the paper, in our paper. So next up, we're going to build a model to describe this experimental data. So we're going to start with the pharmacokinetics, so how the drug distributes through the body. So we're going to start with pembro, and we found pembro was best described by a 2-compartment PK model. So meaning the drug just gets delivered into a central compartment, it can exchange with a peripheral compartment, and your differential equations just capture that movement and the sort of difference of the volume of distribution in the 2 compartments. And you can see over 2 different doses considered, this model well describes that data, so you don't need anything more complicated than this. For bevacizumab, we actually found that a simple 1-compartment model was sufficient to describe the data we had. So here is data for both subcutaneous and intravenous injections, and the 1-compartment well describes the dynamics of the drug. So now we know how the drug distributes through the body. We're going to look at what the drug does to the tumor next, so the pharmacodynamics. So the model we have is just a single equation describing the evolution of the tumor. The tumor is going to be growing logistically. And then you'll see 3 separate kill terms in the tumor. So each monotherapy has its own Michaelis-Menten kill term that saturates, and then you have a combination term. And it's color-coded, so you can sort of see how the parameters were calibrated to each data set. The control data was used to calibrate the growth rate and the carrying capacity. And then the monotherapies were used to get those individual parameters, and the combination data down here in purple got the combination parameters. So we can see this model can sufficiently describe this data, and that then leads us to our question, which is, can we identify optimally synergistic combinations of these 2 drugs? So that means we perform our Pareto optimization in each of the 4 multi-objective synergy spaces.
Sorry, Jana, can
Yeah.
you go back to the slide before?
Of course.
So to model the drug, the 2 drugs.
Yeah.
You have a term for drug 1,
Yeah.
a term for drug 2, and then you have a term for the interaction of the 2
interaction,
drugs.
Correct.
Okay, thank you.
Exactly right. So if K3 is 0, effectively, right, there's no interaction happening.
So if K3 is 0,
Yeah.
what does where is the curve? Like where would the how big is
Big is the
K3?
effect.
Yeah.
K3 is quite small.
It's quite small.
It's quite
So it's just a tiny adjustment.
It is.
Yeah, okay.
It's at least an order of magnitude smaller than the K2s. I think it's actually 2 orders of magnitude smaller, if I remember correct. Of course.
So, thank you. So I don't know if it would be follow-up counseling question. So, for purple, for combination therapy, so it's exactly like, so tumor gets shrunk, yeah?
Yeah.
So it's
Still
my
growing,
understanding.
it's just
Yeah.
smaller than without
Yeah.
growing.
So it's growing, but it's more flat
Exactly.
than in the control case when there is nothing involved. Yeah.
Yeah, exactly.
Okay, so it's basically same thing as Kaslinas, or not? So is it the same thing? No, you were asking something technical about differential equation.
Yeah.
So mine is about like the
Yeah.
graphs.
Just the one therapy alone, the other alone, the combination together.
So,
If you don't consider the interaction between D1 and D2, so that K3 parameter is 0, the purple curve almost looks about the same. So there's just a small correction
Yes.
because of the interaction. Yeah, that's what I was asking.
Exactly.
means there is interaction curve.
There is an interaction
Yeah.
term
Exactly.
that they've modeled, yeah.
That's
Yeah.
exactly right. You got it. So now we're in each of these 4 multi-objective criterion spaces. And what you're going to see is we tested a set of combination protocols. Anywhere you see a blue dot is a combination protocol that was not identified as Pareto optimal. Anything that's red is on the Pareto front. So in that multi-objective synergy space, right, those points on the red points are being identified as Pareto optimal. What you can't tell from looking at this is which doses they correspond to. So what we're going to do is take this and map this back into dosing space. So there's a lot of data to see on here at once. So let's talk about it. Horizontal axis, the dose of Pembro. Vertical, dose of Beva. The color is the model predicted tumor growth inhibition relative to the control. So that dark blue would mean 0, which means you're behaving just like the control. Bright yellow, 1, tumor's gone. The volume is 0. So those are the model predicted colors. That red star is the experimental dose. Then the numbers you see indicate how many times that dose was Pareto optimal. The largest number you could have is 4, meaning every one of the criterion spaces selected this as Pareto optimal. If you don't see a number at all, it was never identified as Pareto optimal. So what sort of jumped to us here is there are 3 different sets of doses in this space that get labeled as 4, meaning it did not care how you defined additivity for both efficacy and potency. These doses are coming out as Pareto optimal. Now let's observe here, these doses are a lot less effective than the experimental dose, but they're also, right, you're much less toxic because you're giving a lot less drug. So go ahead.
Sorry, Jana, would you mind explaining how you created the curves on the left? Yeah,
Yes.
thank you.
So every one of, this region is discretized. So we end up testing, which I think here ends up being like a 12 by 12 grid. And we literally test every combination therapy. So we know how much drug went in and we know the efficacy by the model. We use those combination index values to put the synergy of potency score on the horizontal axis and the efficacy on the vertical. And then you literally just find the points that meet the Pareto criteria. So it's literally just a manual search of these points. So anything that sort of satisfies the criteria of you can't make one bigger, one smaller without making another bigger gets selected as red. Does that answer? Great, you're welcome. So once you have these doses in front of you, you then get to make a choice still. So if you're trying to maximize tumor growth inhibition, you'd go as far into the yellow region as possible, right, to get as much efficacy as you can. If you're trying to minimize toxicity, you take as little drug as possible. And then, of course, you'd have to look at this profile about how toxic it is versus how efficacious. Is it efficacious? how efficacious it is, and make a go or no go decision based on the outputs you see. So this was sort of our original implementation of the algorithm. And I was here at the Fields Institute like a year and a half ago and was asked a very good question by Kathleen that stuck with us. And we've made some changes to this algorithm since then. So one of the things that she observed was that the notion of Pareto optimality is binary, right? So you could be incredibly close to that front, effectively have the same combination index for all intents and purposes, but you're not identified as Pareto optimal. So what we decided to do, right, so sort of to take into account for the fact that those are effectively the same, we introduced the notion of near Pareto optimality. So the extent of these spaces depend on the metric, like how big the domain is on each axis. So we just basically measure the extent of the region and then define anything within some epsilon distance from that to be near Pareto optimal. So if epsilon were 0, you recover the Pareto front. If epsilon were 1, you select every single point in the space. We ended up using 2%, 0.02, as our metric. And the effect is that some other points, you can sort of see these in the red square, get selected as Pareto optimal as well. The other thing we decided to consider when we're going to sort of move forward with this algorithm is that we sort of implicitly imposed constraints on toxicity by putting an allowable upper bound on each drug. But we weren't considering any minimal efficacy when we did this. So you'll notice there's a bunch of points here that really lack any meaningful efficacy, and some of them get identified as Pareto optimal. Now, you can certainly just not use these doses, but mathematically, it actually makes more sense to constrain your space first and then do the optimization. So that's what we'll do. We'll introduce a minimum sort of efficacy threshold of 60% inhibition relative to the control, remove any of those points from the space, and then perform your optimization on that space. So with those two changes made, we were ready to really do the next thing we wanted to do with this was move from thinking about the average mouse in these experiments to thinking about heterogeneity. So here's how we're going to go about doing this. We're going to consider a parameter cuboid where 3 of the parameters in the model are allowed to vary. And the 3 we chose are all basically the tumor kill, right? The rate at which the tumor is killed in response to the 2 monotherapies and the combination therapy. So we're assuming then the control parameters are fixed in this case, as are the IC50 values. And what we're going to do is we're going to determine a sort of an allowable domain for each of those parameters based on what we saw in the experimental data. We introduced some criteria to get bounds on each of these parameters. And then what we're going to do is break up each parameter, so each of those axes, into one of 4 categories, classifying any parameterization, which I'll think of as an individual mouse, as either being a minimal responder to that particular therapy, either the mono or the combination, a mild, moderate, or a strong responder. So what this does is create 4 cubed or 64 potential regions you could be classified in. So it's not going to be a strict personalization approach, but it's going to be semi-personalized, and I'm going to care which of the voxels in this space you fall into. So what I first want to show is that the voxel you're in matters. Not that this would surprise anyone, but I still want to show it. So on the left, you see the same results from earlier in the talk, just with the 2 changes made to the algorithm, so near Pareto optimality, as well as constraining space first. And what you see is at the baseline parameters for the average in the mouse, the experimental dose right over here is selected as Pareto optimal 1 time. If we didn't do near Pareto, that's never selected as Pareto optimal. If you then look over to a mouse that is more sensitive to bevacizumab, suddenly the experimental dose is always Pareto optimal in every 4 of the spaces, right? Just to demonstrate, right, that your response, right, really does depend on where you fall in this parameter space. So that being said, we wanted to quantify this more broadly. So we have each of these 64 voxels. In each of them, we are going to randomly sample 30 parameterizations. And then we want to understand the response of those patients in that voxel. So we run the algorithm, the optimization algorithm, in each of the 4 criterion spaces for all 30 of those patients. And then we're going to calculate what we call the Pareto optimality score. So I'll show you how that gets calculated. So the 1 sub p is just an indicator function that will return the value of 1 if sample m in voxel I for criterion space n is Pareto optimal. And you normalize that by the number of times you're doing this. So if you get a value of 1, that value tells you every single individual in that is identified, has the combination you're looking at as Pareto optimal in every criterion space. So very robust prediction. If you got a value of 0, it's never Pareto optimal. So the value between 0 and 1 is a normalized metric to tell you how robustly Pareto optimal a combination therapy is for patients with that specific set of features. Bova.
I'm actually sometimes asking technical questions, but my PhD thesis was on Pareto. No, it was exactly on Pareto type distributions and large deviations. Yeah. So, but I certainly would share what I know with you. I'm just wondering about script P of I, which is clearly like a measure of robustness.
Yes.
Would it be something like cumulative distribution function for Pareto type distributions or not, or you have never thought about it?
No, okay, my instinct says no. To be honest with you,
because I understand it's a score, yeah.
Ability, honestly. So this measure is a little harder to interpret than I'm sort of leading on. So let me give you an example. If I got a p-value of 0.5 here, that could mean every single patient sampled in here was Pareto optimal, but only in 2 of the criterion spaces. It could also mean that half the patients were Pareto optimal in all 4 spaces. So the number is a little weird to interpret. 1 definitely means robust and 0 definitely means not, but the in-betweens, it's not quite a strict, I mean, it's a probability in that it's between 0 and 1.
For p-values,
but I wouldn't think of it as.
But like for p-values close to 0,
yeah.
Have you looked at it? It's probably it's too technical. Yeah,
It says I don't think of this as being related to a cumulative probability.
I'm very bad at asking technical questions.
No, well, we can talk about it offline too. Yeah. So what I want to do now is just sort of show you. So across sort of the different semi-personalized voxels you could be in, what you're going to see on the right is the corresponding value of the Pareto optimality score. If an area is blacked out, and I'll start playing this. If an area is blacked out, that means those doses did not meet the tumor efficacy threshold, right? The TGI threshold to be considered in the optimization. If you see bright blue somewhere, that means it's a robust prediction, robustly Pareto optimal for individuals in that voxel across criterion spaces. And what you could start to watch here is how as you move across, right, sort of the voxels, depending on the type of patient you are, you could see where the best combination therapy by this measure is going to fall, right? So we do see sort of a lot down here, but you do see it jump around the space. So it gives us a way to really sort of quantify based on who you are, which combination would be robustly Pareto optimal for you. And that's only sort of one way of thinking about the problem. Another way of thinking about the problem is you have a dose that you've already pre-selected, and you want to know the right patients for that dose. So we can watch that play out as well, where we look at the dose on the left, and on the right, you're going to see the patients in each of the voxels. Now a value of 0 is shown in blue. Those are people who don't respond well to that combination if we're looking to optimize synergy. When you do see bright yellow, those are people who respond very well to the combination therapy that we're looking at. They have a Pareto optimality score near 1. So, right, if you have that dose specified, a yellow patient is the ideal patient for that drug, that combination is the way to look at that. It's obviously a lot of data to take in, but sort of the natural follow-up question then becomes, well, if you have a patient in front of you, how do you know which voxel they fall in? Now, this is all mouse data, so we're still talking about preclinical experiments here. But these parameters are not something you can get from a measurable biomarker. So we need to introduce an experiment to be able to get access to the value of these parameters. So we introduced what we call an initiation protocol, which is a way to sort of confidently determine the value. Sorry, can you describe the dynamics in patients where the voxel with the highest score is not touching? I can't read the whole thing.
I can also just ask the question. Is that
okay? Go ahead. Thanks.
Okay, so in the animation you were showing, there were no, one further back.
Okay, cool.
Okay,
Go ahead.
yeah, in this one. There are patients, there are voxels where the highest scoring grid is not touching the black mask for the efficacy. Like this one, for example.
Right, yeah, it doesn't touch the boundary of the region, correct.
Right, yeah. I just want to know, do you know what dynamics this particular parametrization of the ODE looks like in dynamics, like in its dynamics? Like why is it that it's not touching the
So the question really, so when it does touch, what that is effectively representing is that the potency, right, the potency of the therapy, so how much drug you're giving, right, is really preventing you from wanting to be in the region further into dosing space where you end up giving a lot of drug. So the regions near the boundary are always the ones where you give the least amount of drug. So since you're trying to really balance both efficacy and potency here, sometimes potency is almost winning that battle and it pushes you to the black region, right? Occasionally, right, well, depending on your parameterization, the potency doesn't win out and you get to move away from the boundary a little bit. So it's really just about sort of the battle between efficacy and potency that sort of plays out here.
Okay.
If that answers it.
Thank you. Yeah, that does.
Right, so the question of, okay, now I have a mouse in front of me. How do I know which voxel they fall in? So here's what we propose to do. We propose like basically an experiment you could run where that experiment, at least according to our model, you could confidently isolate the values of the 3 kill parameters and therefore be able to place them in a voxel. So here's how that works. You'd plant the tumor cells, you let the tumor grow, and you take a measurement of the tumor volume as your baseline, and you administer the drug with the shorter half-life. You wait for that drug to effectively clear, which we define as being below 90% of its maximum value in the plasma. Take another measurement of the tumor volume. At that point, if you're only trying to measure one parameter, you're assuming everything else is known. That you could see up here that we could confidently predict the value of that kill parameter. So what you're seeing is on the horizontal axis, the values of the parameters, the vertical axis is the cost function. And what you can see is there's a clear global minimum in the cost function representing a practically identifiable parameter. So, okay, if we do this, we could get the value of K2, D2 for that mouse. You then administer the next drug. You wait for it to surpass its Cmax value, you take another measurement. Under the assumption the first drug has cleared out, then you can confidently determine the value of the kill parameter associated with that drug. Give the combination therapy, wait for both to pass their Cmax, measure again, because you already know the monotherapy response, then you can uniquely determine the combination response. And here you can see the values, the orders of magnitude. These are around 10 to the -1. This is around 10 to the -2, the values of the parameters. So now we have a prediction about which voxel that mouse would fall in. Once you know which voxel they're in, then the algorithm just outputs what is the Pareto optimal combinations for you. So for this particular mouse, you get 2 therapies very close together. Both give the same dose of Beva, slightly different dose of Pembro. You can see it's not very strongly Pareto optimal. It's not a score of 1. It's about a score of 0.67 is the best we can do for this patient. And you can see the tumor growth inhibition also predicted by that combination. So now we have a way to learn using the model, right, where to classify you and then how to best treat you if your goal is optimizing synergy. So to wrap this part of the talk, right, this was really just a method to optimize 2 forms of synergy in combination, right? So both efficacy and potency. Code's freely available on GitHub. And this was really all about how do we make robust predictions from our models. To do this, you need data, but you don't need an incredible amount of data. You need PK for both your drugs, and you need tumor volume time course for the control case, the monotherapies, and the combination therapy. And we're sort of thinking about how this could be expanded if you don't have preclinical data where you have tumor growth inhibition measured, but instead had clinical data. So that's sort of the first thing I wanted to tell you about. The second thing was more about the question of how do you get the right data for your models? So the question we're really asking, to be more precise, is as follows. what is the minimal amount of data you need to collect so I can confidently determine parameters in an ordinary differential equation model? So the context we're going to do this in is a site of action model of the immune checkpoint inhibitor that was in the first part of the talk, pembrolizumab. And the tool we're going to use is identifiability analysis. I'll tell you about the tool, then the context. So if you haven't seen it before, identifiability analysis asks the question, can you uniquely determine your model parameters from data? And structural identifiability asks this question in the context of perfect data. So just to sort of illustrate with a toy example, if this was your perfect data and for some reason you are fitting a 3-parameter line to the data, we all know that obviously you are not going to uniquely determine the value of your 2 parameters because anywhere in this case where A times B gives you 2 is a perfect fit. Easy fix, right? You reparameterize your model. Now you'd have unique values for your parameters. Obviously, this example makes it look trivial, but if you have a large system of ODEs, this isn't always obvious from looking at the structure of your equations. That said, a natural question would be, why would I care? You never have perfect data in biology anyway, but it ends up that structural identifiability is a necessary condition for practical identifiability, which asks this question in the context of real and noisy data. So we're going to assess practical identifiability using the profile likelihood method. So the way this works, if you haven't seen it before, is you pick one parameter in your model at a time. You set a range for that parameter. Take a value of the parameter in the domain you've set, fix it. Then optimize the rest of the parameters in your model. So whatever cost function you have, you're going to minimize it, given you fix the parameter at this value. Record the value of that cost function. Repeat it over a discrete set of values in your domain. That creates what we call the profile likelihood curve. And under some assumptions about normality in the noise structure, you can compute confidence intervals for the parameter as well. So how do we interpret these things? So the ideal outcome is that you have enough data to determine the value of your parameter. And profiles in which that happens look like this one. So there's a clear global minimum in this. If you move away from that global minimum, the cost function increases quite quickly, and you cross over the confidence threshold on your domain. So we will call this practically identifiable. There is enough data to know the value of this parameter. The extreme other end of the scenario, you get a completely flat profile. So if you think about what this says, it's that the data is completely non-informative for the parameter, because no matter what value I take, the other parameters can compensate and I fit equally well. So we would say this lacks structural identifiability. Then you have the in-between case. You are structurally identifiable, you're not practically identifiable. Our goal is to use identifiability as a tool to inform experimental design. So if you're thinking ahead a little bit, you might think I just sort of talked myself into a circle. You need data to do identifiability analysis, but somehow I'm going to use identifiability analysis to tell you what data I need. So the methodology I'm going to show you is going to sort of handle this seeming contradiction, and I'm going to illustrate the method in a specific context, but also try to demonstrate its broad applicability to you. So now the context. So to understand this part of the talk, I need to tell you more about the drug. The drug, pembrolizumab, didn't really matter in the first part of the talk, but now it does, and you'll see why after I tell you a bit about it. So very quick primer, immune cells, T cells express checkpoint molecules. When the checkpoint molecule is bound by its native ligand, a signal is sent to the immune system to tolerate whatever is bound to it. The problem is tumors express the ligand, so it sends a signal to the immune system to tolerate the presence of cancer. So what do these checkpoint inhibitors do? They come in, they disrupt that native signaling. So you no longer send the dope kill signal. That could wake the immune system up to try to target the cancer cell. Okay. So what I hope that sort of very quick primer illustrates is that the efficacy of this drug is going to actually depend on to what extent the drug engages its target in the tumor microenvironment, because you need to wake up the T cells in the tumor microenvironment. But the problem is, when you actually look at the data that you have available to parameterize these models, it's typically going to be plasma drug concentration over time and tumor volume over time. In other words, you don't typically get measurements of how much the target is engaged in the tumor microenvironment. So that led us to the following experimental design question. How many measurements of percent target occupancy in the TME would you need? And when should you collect them so you could confidently determine the parameters in your model and therefore have more confidence in the predictions made from the model? So the model we built of Pembro earlier in the talk is not sufficiently complex to answer this question. So because our question now requires knowing more detail about the mode of action, the model needs to get more complex. Before, you might recall, we had a central and a plasma compartment, but now we're going to introduce a third compartment, the tumor microenvironment. And unlike typical compartments where the volume of distribution is fixed, this volume of distribution will change as the tumor grows or shrinks. And we keep the pharmacodynamics the same as before in that the tumor just grows logistically and is going to be killed by the drug. The only difference now is that when it's killed by the drug, we don't want the plasma drug concentration to determine tumor killing. It will depend on the binding of the target to its receptor in the tumor microenvironment. So when you see the tumor equation down here, same form of the kill term, but now it depends on percent target occupancy in the TME rather than drug plasma concentration. And even though there's only one drug here, we now have 8 differential equations instead of just the 3 we would have had for one drug before. And this is because you now need to account for the dynamics of the target in the compartments, whether it's bound or unbound, and it increases the number of compartments. So new model, need to recalibrate it. So here you could see calibrated fits to both the PK and the PD data at doses of 10 mg per kg. We would fit to that. This is more just a prediction, not a fit. There was a publication that looked at percent target occupancy in the TME as a function of drug concentration. And we can see we sort of follow that data. The data is very messy. We held out some data to sort of just confirm our parameterization on. So PK at a dose of 1 mg per kg, PD at a dose of 2 mg per kg. The model can well capture that. It wasn't trained on that. So, okay, we have a model. But you saw it had 8 differential equations. That means it has 20 parameters. And I could promise you without doing any work, these parameters are not all practically identifiable. We all know basically systems biology models contain a large number of parameters that are not practically identifiable. So at this point, we need to narrow down the set of parameters we're going to consider for the study. So here's how we're going to do the narrowing down. First of all, if anything can be readily estimated from experiments or literature, we're going to take those estimates. So for instance, PK parameters, they're pretty good ways to estimate these things. So we're not going to pay attention to those. And if you have a parameter that the model output is just not sensitive to, there's no reason to consider those. We'll just fix those at some value. So then, sort of keeping that in mind, we performed a really simple local sensitivity analysis. We let each parameter vary by 5%, and we look at the change in both tumor growth inhibition and percent target occupancy in the TME. And the higher the bar, the more sensitive you are to that change. And it ends up the same 4 parameters were sensitive on both, very sensitive for both metrics, and we're going to take 2 of them for further analysis. The drug target binding rate in the TME and the rate the target is synthesized in the TME. We chose these 2, not only are they both very sensitive, but also because they're things you really could never get good experimental measurements on. So once we have those parameters, what are we going to do? We're going to allow these parameters to vary. So we're going to introduce uncertainty in these parameters. We assume they follow some underlying distribution. Every other parameter in the model remains fixed. What we're then going to do is randomly sample values from these distributions, and we're going to take these values and put them in the model. The model knows, it knows the equations, it knows the other parameters. So what the model can do is then predict the variable of interest for us, which is percent target occupancy in the TME. So these are model predicted values of percent target occupancy as a function of time. We do this 10 times, and we're going to treat this as it is 10 data sets for percent target occupancy in the TME. Now, no one's measuring this for you continuously, so we're going to discretize this daily and assume that is the ideal experiment. The best someone can do is measure this for you every day. And then ask the question, in the ideal world, someone could do this for you, could you identify these parameters? And the answer ends up being yes. So if someone performed this experiment for you, right, you do get nice parabolic profile likelihood curves, which says, yes, if someone can do this experiment, we can determine these parameters. Only then are you ready to ask your experimental design question. That is, what's the minimal amount of data that preserves this feature? So to sort of step back and summarize what we've done, we identified our experiment, measuring percent target occupancy in the TME. We proposed a site of action model, detailed enough to answer the question, hopefully not more detailed. We identified 2 parameters for further analysis, use them to get simulated data, confirm the identifiability in the ideal scenario. If you didn't have it, you couldn't go on. You need to go back and redesign your parameter set. And now we're ready to ask our experimental design question. So the first thing we did was say, well, what if someone can only measure this for you once? So there's a lot of data here, but the way to read it is that the black profiles are if you had the measurements taken daily, the nice parabolic curve. The colors are the profiles you get if you only had 1 day of data. So the blue ones are when the data collection happened early in the month, yellow data collection happened at the end of the month. And if we focus on the parameter on the right, the synthesis parameter, you'll see that none of these profiles are practically identifiable, right? They don't cross over the threshold on the domain. So that tells us, right, that there's not enough information in that 1 data point to determine the value of that parameter. It's even worse if you look at the binding rate. The profiles appear effectively flat. So there appears to not even have structural identifiability. It's not truly flat. It just looks flat on that scale. So then you go, okay, so now it doesn't seem like 1 day of data is enough. I want to show you the problem that sort of propagates forward in the model when this happens. So I'll go back for a sec. If you actually consider all like sets of parameters that are within the 95% confidence interval, so these are parameterizations that well describe your data point, and then propagate the model forward. So over those parameter sets, predict the tumor volume. So the star is the actual experimental data, and the colored region is what the model predicts the tumor volume would be over the set of plausible parameters. And what you could see is if the experimental measurement came at day 1, you effectively have no predictive power in your model at all, right? The tumor could go to 0. The tumor can grow by orders of magnitude. The error in not knowing that parameter has propagated forward so much that you can't predict the tumor volume anymore. If that measurement happens in the middle of the month, we tighten the predictive region, which is nice. You do miss the data, not by a huge amount, but you miss it. And if you take the measurement at the end of the month, at least we know the tumor is growing. That's better than day 1, but it's an absurdly large predictive region. So you can see how uncertainty propagates forward in the model when you don't know your parameters well. So 1 day of data collection won't do. We consider 2 days next. So there are 32 ways we can have 2-day protocols designed. Here are the profiles that result from that. It seems like, okay, we definitely get structural identifiability. To see if we have practical identifiability, I'm going to show you the data a little differently. Horizontal axis when you do the first experimental measurement. Vertical is when you do the second. Nothing here because the second comes after the first. The marker is going to indicate how many parameters were practically identifiable for that experimental design. And you'll see this whole swath of space that are these orange squares where neither parameter would be identifiable. Most of the space is either that or 1 identifiable. So as sort of a general rule, 2 time points don't seem sufficient to determine the value of these parameters. That said, there are 6 exceptions in the space. Those are highlighted by the blue circles. And I do want to show you because it's sort of cool to see. If you take parameters predicted by one of those 6 protocols, look how tight the predictive region is. So the uncertainty doesn't propagate forward in the same way, which is cool to see. That being said, still wouldn't recommend one of these protocols because the design is not robust. Take one, come a day early or a day late for your measurement, it's gone, the identifiability. So given that, we do not want to recommend a 2-day protocol. So we moved to 3-day protocols. There's a lot of them now. So rather than test them all, we're just going to sort of randomly take 28% of them and look at the profiles. We seem to have identifiability, but it's hard to read. So what, Kathleen?
Sorry. Like, is the fact that it's not sort of like a continuous smooth region for your identifiability because of the dosing of the drugs and the differences between the sampling and the dosing and your hitting or missing dynamics in the
so
drugs?
I do think, and especially that you'll see in the next one, the sensitivity to the first measurement is very much about the fact that the experimental protocol was giving drugs every 3 days and you had to wait long enough after the first dose. And if you waited too long, you lost the effect of it. So I do think, yes, it's quite sensitive to the design of the actual experiment. Yeah, good question. Okay, so these are the 3-day ones. You cannot at all tell how many profiles are identifiable here. So I'm going to pull just those out to look at. And it ends up it's only 7% of them. So it was not a common occurrence that both parameters would be identifiable. But looking at these profiles, the colored ones compared to the daily data collection in black is really interesting. So first of all, the global minimum, the best value of the parameter, is effectively the same, right? The prediction you'd make, whether you have 3 days of data or 30 days of data. Even cooler, if you look at the confidence interval, so like the spread of the curve, it's not much larger with only 3 days of data. So you don't introduce that much more uncertainty with only 3 days of data, which I thought was pretty cool. So we like these, but we still don't know it's robust yet. So I want to look at where these protocols are in space. So now we're in 3D protocol space. If it's colored red, they were not both identifiable. Blue, both parameters identifiable for that protocol. And to your question, Kathleen, notice the blue, it almost falls along a plane practically in this 3D space. And that plane does require collecting data on the 4th day. And that's sort of a strict requirement. And then the second measurement had to happen by day 16, according to that. So what we're going to do is project onto that plane, because that's where we really need to be, and look at all the ones we happen to sample in that region. And you can see a lot of blue, both identifiable, but it's not a guarantee. It's about 90% of the points. So since it's not a guarantee, we then looked through the space, just manually looked through it, and ended up identifying this region right here. Everything we randomly sampled was practically identifiable. So we're going to now look at that region, but test every protocol in there. And it ends up that every protocol results in practically identifiable parameters. So this not only confirms the robustness of the prediction, but also that you don't need to test every protocol to actually use this method. So to sort of summarize what we would recommend for the experimental design scenario, if you want to confidently be able to measure these parameters, you need to measure percent target occupancy in the TME 3 times over a 30-day period. The first sample needs to be taken on day 4, but then the second sample, you have a lot of room. Anywhere between day 5 and 10 will do. And the third sample, anywhere from day 16 to the end of the month. And this was the largest region of the space we could find that will result in all your parameters being practically identifiable. So, right, this is really a methodology to really ask the question of how do you get the right data for your models. The method does require communication with experimentalists because you need to know what experiments you could actually run, when you can run them, what they cost, and so on. And we hope approaches like these can really align models and data in a way that increases the efficiency of experimental design, but also what you can get out of your models. So can't end without thanking my partner in crime on both of these projects, Irina Kareva, and our time together at EMD Serrano and NSF, who helps support our computer cluster that all these things get run on. And thank you all for your time and attention.